All right, welcome to Module 3. This is Part 3, and this is talking about functional structures and the ideas of law conservation of energy being applied to buildings. And so here we go. This is that same McCoskey Center that we left off with in Part 2 of the videos, and this is some more of what they have going on at this building. Another piece of the structure is this building right here. This is a natural water spring that was coming up out of the earth, and groundwater tends to come up out of the earth at a temperature of about 55 degrees Fahrenheit. And so what they did is they capped the spring that was coming up out of the earth, and the water kind of drains off into the garden regions here, this natural spring. And we use this as a storehouse or a cool house where we could make it into a rock refrigerator, right? So we were using those 55 degrees, and up over where the spring came to the surface, we have shelvings and things like that that held veggies and other produce in a natural refrigerator structure. On top of that is a living roof system. We grew small plants and legumes and other things that were hardy and very tolerant of the sun. And at the time that I was in this degree program working on this, we hadn't got into green roofs. So this predates the green roof revolution. And this is one of the early experiments of small, high slope green roofs. And I got to be a part of that. So it was a nice little bounce. And some of the people that I was in school with at that time have gone on to be big names in green roofing. So there you go. Here I am as a lovely stinky college hippie, right? So eventually I graduated, got my degree, and shaved my legs and joined the real world. So here I am back then. Down below is some lovely batteries, so some outdoor deep cycle batteries. Those are hooked up to that solar panel that you saw on the roof, and this is just a general battery system. This is a little control system that we built up, and it's one of the systems that I built to do some simple purpose stuff. We had a simple washing machine so we could wash some clothes and just do things, and that's what this was doing for us. That's what this system was built for. It's one of the things that I will show you how to do later in the chapter. I want to empower you so that you know how the big systems work, so that if you ever go to work in the industry, you get to be a part of those big systems. But I also want you to feel empowered that if there is a small project that you want to do, a small purpose that you want to create, I want you to feel comfortable enough to take on that project and do that experiment and build that little system that you need. And so this will be something that I'll show you how to build your own little solar tractor, your own little mobile solar system. Here's the big solar panels that we ran the building on, as well as one of the larger wind turbine structures down there. And this is a gray water system. Since it was a sustainability practice building, we had water that had to be pumped up using our stored power, and that water could not go into a septic system because we were trying to reuse it. And so this is gray water. So with that said, it meant that going to the toilet wasn't allowed, and we had a composting toilet, and I will show you that in a moment. Here is another, this is a solar tractor system. It's mobile. It allowed us to move it around. It was great because if we moved the chickens or livestock to the other side of the little farming area, it gave us the ability to electrify the fence so nothing would come and eat our food that we needed to eat. Here is one of the wind turbine structures. And we used to do workshops with wind turbines, and I will show you more of that because I've built a few in my lifetime. And I'll show you those small ones that I've built, and I'll talk about the big systems that exist and the different companies that are producing those big systems and how we install those as well. This was a autoclave style oven. It was a high heat oven that had thermal capacity on either side, so it would heat the air, and air can be a great insulator. Think of a down coat. How does a down coat work? Well, it's not the feathers that are keeping you warm. It's the space, the air that the feathers create around your body. And so when you put on a down coat to stay warm and the wind comes by, it blows away the exterior, but it keeps the heat of your body heat. So you are self-warming. This is a self-warming system where we would burn in the morning in the winter when it's cold, and it would heat up these chambers, and that would radiate heat like a radiator system all day long. And then we would burn again in the afternoon if it was really cold, and once in the evening. So we would burn 3 times a day for high heat. And if it was really cold in the building, we needed to warm it up quickly. Since this was the burning area, you did not open that. You locked that shut, and it burned really warm, around 2000 degrees Fahrenheit. And then up here was like a little oven thing. We would also cook pizza in there, good stuff. So that little oven up there, we would then take and open that up, and that would allow the heat to just come radiating out so we could heat up the building really fast if need be. And that brings me finally to the composting toilet. I said that everything in the system needed to be reused. That included water, which meant that we couldn't put our fecal matter into the water system since that water had to be recycled back. And so this is our composting toilet. And you would go to the bathroom, and then you would add a scoop of wood chips to it. And down below, it would drop into the chamber, and down below, it would be composted viva microbes. So we would do an aerobic microbial system. Aerobic microbes are the non-stinky ones. The anaerobics, the non-oxygen-based ones, are the ones that make the stinkies, the methanes and things. So we kept it aerobic with a venting system. And we basically would compost our fecal matter, and at the end of a certain amount of time, the fecal matter would drop into the chute, and it would just be black dirt, and we could use it. Now, with that said, the stuff that would drop into the chute would be stuff that we wouldn't use on our food gardens, because if we did, they would not be organic, because I can't guarantee that you as a human using my toilet were organic. You didn't take headache medicine. You didn't have any type of prescription. You didn't happen to consume anything that was non-organic yourself. And so because of that, we couldn't use it there, but we would use it in like ornamental areas of the farm facility. Bringing us into conservation efficiencies. This brings us into efficiency ratings of products. So efficiency is a calculation on how good everything is compared to losing it to other forms that we don't want. So efficiency is the total of all fuel, air, water in the system equal to all the electricity, water, and combustion gases that come out. And that creates our overall efficiency within the product. The way we would do the equation is efficiency is equal to 100% times all useful energy divided by all of the input energy that we put into the system. This is a little graphic that shows us a little bit of the efficiencies of various systems. And notice that when I add in more steps to my system, I lose efficiency, right? But I also want to point down here at solar cells. Solar is incredibly inefficient. We don't use nearly as much of the sunlight spectrum as we could and should use. We only use the parts of the spectrum of sunlight that is most common. And I'll talk more about that later on. But I want you to also see that there's room for these sustainable materials and things that we're coming out with to improve as well. So everything can use an improvement. Everything has some inefficiency in their systems. This is that lovely talking about the efficiency and the overall efficiency of that light bulb. If you take it all the way from the power plant and you move it through the actual production of electricity within the plant, so we're putting it through a generator system, which then is turning, it's going to be the fuel, which is burning. The burning fuel is heating water. The water is turning steam turbines. The steam turbines are turning the generator. The generator is making electrons jump. The electrons are being forced out onto the grid. They are sent through transmission lines. And then finally, through those transmission lines, they are sent into your home, which then they become the little light of the bulb. And when I move through all of those different stages of efficiency, the overall efficiency that I get is about 1.6%. And so that's highly inefficient. And that brings us into the argument for smart grids and all of those projects and programs that we're talking about. And the truth is our infrastructure in the US is aged, and we really could use a lovely upshot. So on that note, I will leave you with this efficiency table, and I will talk to you again in Module 4.